Yes, this is the same. So I can say this is x component whole square, this is 2t whole square plus 4 whole square plus 4t plus 4t minus 6 whole square, right? So you can calculate this value very easily, okay? And you can just divide this value by the vector that we have represented here, if you divide this vector by this quantity, then you get the unit vector along the tangent, and or you can say that the unit vector along the tangent can be represented by this is t cap, and you can simply write this way, that is dr vector upon dt, and this is dr vector upon dt, okay? So, and you can calculate this result, and easily you can divide, and you can keep the sense of the vectors, that is I, j, k same, and you can find the vectors. So depending on these questions, so probably, since I have decided that I will give a lecture series on this one, so I'm giving you a questions as a homework. So I have no idea whether there is a discussion forum on the website or not. So probably if you have any questions regarding anything, so I can discuss there as well. So probably I give you an example to solve for you to try on this same matter, so you can easily find this also. So I'm giving an example. Find the, and this is for you, find the angle between, and I think similar questions like this, or just lower level questions like this, you might have solved in your elementary classes, right? So find the angle between the tangents, find the angle between the tangents to the curve, and that is r vector, which is equal to t square I cap plus 2t j cap minus t cube k cap at the point t is equal to plus minus 1. So you have to find the angle between the tangents to the curve, and the curve is represented by this equation, and so you have to find the angle between the curve and the tangents at the 2 points, that is plus 1 and minus 1, right? So this is a question, again very simple questions, which I have just talked about just before, and you can use your basic concepts to solve these questions. And probably if you can't, then just ping me, probably I would be able to do it for you, okay? So, and this is where we end this portion as well. So now moving to the next portion. Okay, so we move now to the different function that is called, what is scalar field. There is a new term which is called, what is scalar field and vector field, okay? So this is our new topic. Okay, so what do you understand by this scalar field, and what do you separately understand by this vector field? So obviously a little notion you can have that the field which is represented by a scalar function, that is called scalar, or you can say that the field which is represented by a vector, and that is called vector field, right? So if I say that if let R be the region of space, so R be the region, and that could be a region of a real number only, right? So suppose this is in an arbitrary space, and which is represented by R, and this is a region of a space, and you can say this is a region of real numbers. So any scalar function, if I say that this is a scalar function which is represented by this in 3 dimensions, that is x, y, z, then this scalar function is called a scalar function of R scalar in a scalar field. Why? Because at each point it will have the same scalarity, or you can say at each point here in the region, at each point it will have the same sense of scalarity, right? So which means that at each point the properties of that scalar function will never change, and that's why that will remain as a scalar functions everywhere, and the field which represent this scalar function, and that field is called scalar field. So these are very small things which need to be understood. What is a vector field? So probably we can understand vector field as well. So if I say this is any quantity which is represented by this v, x, y and z, okay, so then v is a vector, then this v is a vector function, and r is, and this v is a vector function, and r is called vector field. Why? Because at each point of region of space the field is regarded as a localized vector. That means that localized vector corresponding to the point x, y, z. What is the meaning of localized vector, right? So localized vector is nothing but it is termed as a free vectors only. It's free vectors only. That irrespective of any points in the regions, its properties of being vector, it does not change into the scalar, right? And it remains the scalar only, and that's why it is called the vectors, and this is called vector field. So if I tell you an example, for example, if just before I told you an example that force depends on the positions and time as well. So the question comes whether the force is a continuous function. It is a the two primary questions comes that whether it is a continuous function of time, or whether it is a differentiable function of time, or whether it is a differentiable function of time, right? So, or many things. So that gives always a doubt, and because of that there are many theories, or there are many abstracts which is being developed, but all those theories in between are classing each other. What is the exact notion of understanding a particular vector, but that result is still one of the area of research which but here in the syllabus we don't need to go into the details of that. We just need to concentrate here on what is in the syllabus. Okay, so these were the two quantities which I really wanted to tell you what is scalar and vector field. So why? Because the next topic is our gradient of a scalar field, right? And this is also, you are familiar, you must have studied in some of the engineering subjects. For example, if you're from electrical or mechanical engineering background, so probably you might have heard what is gradient of a scalar field. So if a phi is any scalar and which is represented by a gain, that is function phi x, y, z, so grade phi is nothing, it can be represented by this way. So grade phi is I cap delta phi upon delta x plus j cap delta phi upon delta y plus k cap and delta phi upon delta z. Okay, so from here you see this this phi vector, which is an scalar field, is obtained. This is only obtained by operating an operator which is called nebula or del. So this operator, you also have heard, this is called either del or it is also called nebula, right? And this del is nothing but this is I del upon del x plus j cap plus del upon del y plus k cap and del upon del z. So similarly we can represent by just summarizing that above equation that we have, that grade phi is nothing but that is operator delta or nebula and the scalar field, that is phi. Okay, so this is what is called grade phi is represented by an equation. Okay, so grade phi is nothing but that is delta and nebula, and this operator is on the scalar field. So you can say grade phi is nothing but that is the operator which acts on in the scalar field, that is phi, and this operator acts along all the three components of x and y and z axis. Okay, so this is where we finishes the gradient of a scalar field, and the next topic that comes is a geometrical. The next topic that comes is the geometrical interpretation of a gradient. Geometrical interpretation of a gradient. Okay, so let us understand that if any surface that is phi, which is represented by this equation, that is f of z is equal to some constant that is c, okay, and we are drawing this two figure, that is this curve, and we are just drawing this curve, and this is phi equal to c, and this is phi equal to c, and if there is an increment with respect to time, so this will be represented by this is phi plus del phi, which is equal to c dash again, okay. So definitely here if you take the point that is p, so this is a directed line along the curve or between the curve, you can say. So this is q, and there will be a normal that will be acting along this direction, and that will be represented by this n cap, right? So and the angle between this is, suppose, is theta, and here the normal, there is a small infinitesimal normal, and that is represented by delta n, right? Okay, fine. So what I mean to say is that if we are considering these two surfaces through p, at which the function value has a phi, and another level surface through q, where the function value is phi plus delta phi, right? Okay, so this r vector and r vector plus delta r vector, obviously this is a position vector of p, and this is a position vector of q. So I can represent this vector, this pq vector is equal to nothing but that is, again you can say this is oq vector minus op vector, which will give the result that is delta r vector only, right? So this is, but now if you see, this is the gradient. If you apply this dot product of gradient into this small increment in the position vector delta r, so this will give you result that is equal to del phi. How? You can represent by the equation which we wrote above, and you can represent this way, that is, this is nothing, this is having any component that is del x I cap plus del y j cap plus del z k cap, right? If you multiply this with just now that we wrote, if you multiply this with this one with respect to phi, so everywhere you can add this phi here and phi here as well. So if you multiply this equation with this one, with this equation, so ultimately you get this del phi, right? And this del phi, but suppose again the same concept, if q approaches to p when the difference of the time is 0, or when the level of the surface is exactly matching to the two at the same point, then this the same equation becomes 0, which means that what does it say, that this del phi is normal to the surface, that is this surface, and this surface is nothing but this is a representation of this phi. So I can say this this del phi is nothing but this is normal, right? And this is normal to the surface, and this is normal to the surface phi, which is represented by equation that is x y z equal to c. Okay, so and there is another geometrical interpretation which says that the gradient of the scalar field, that is phi, is a vector normal to the surface, or you can say, and is a vector normal to the surface, and its magnitude is equal to its magnitude, which means that if I say this is del phi upon del n is nothing but this is equal to the rate of change of phi along with the normal, right, or along this normal. So this is our next geometrical interpretation that we need to see in the next class, since we don't have the time. So we stop here, and related to so many theorems and so many results that we have obtained here, and so many basic things which we have studied, we will solve numericals related to this one. So, and generally we will also see how we can correlate all these concepts together, and we can generate new concepts. Okay, so I enjoyed my experience here, and probably I hope you also have enjoyed. And if you have any doubts, and if there is any discussion forum for this classes, so I would like to express more and more for you guys. Okay, thank you so much.